sir. Very clear, sir. Sir, we will wait
Okay.
2-3 minutes more, sir. Other participants may join, and
Sure.
afterwards I will give introduction about you to our participants. Then we will start, sir.
Sure, sir. No issues.
Thank you, sir. Thank you.
Thanks. Thanks. Thanks.
Excuse me, sir. Professor Anand Kumar, sir.
Yes, sir.
Sir, do you want to check the slides, sir, now? Presentation. Shall we check now, sir?
Yeah, no issues. Maybe
Yes.
I'll start sharing the screen.
Yes, sir. Yes, sir. Yes.
I think, okay, yeah. Now I can present.
Yes.
So is the slide visible now?
Yes, sir. Visible. Perfect.
Okay. Thanks.
Sir, time being, just to stop sharing for slide, sir. Our
Sure.
admin team will share.
No issues. No issues.
Thank you. Sir, Rajesh, sir, now you can share our screen, sir. Yes, sir.
Yes, sir, I have shared, sir.
Okay. Sir, Rajesh, sir, shall we start, sir?
the science as well as the other allied areas. My intention here is to focus onto the mechanical engineering application. Okay, so that is the background and the brief intro about that particular title. So I've organized my talk in this format. So I would be starting with the part one, where I will try to give the introduction for this nanostructured materials, and then what is the significance, especially from the surface nanostructured material point of view, and what are the processing steps required then get into the scale of nanostructure, which we call it as a nanometer, and this is exactly is our you know topic of discussion today. And also I hope this workshop is also focusing on this particular nanomaterials or the nanostructured materials, right? So now quickly to get the feel of how a macro structure would look like, right? So this is a macro structure of a titanium alloy, and here you can see that this is the micron marker bar, where the scale will depict in terms of millimeter, right? And then you can see that the feature that you see in this macro structure, these are all we can call it maybe a grains, and then there are grain boundaries, right? So on and so forth. Different features can be obtained as we zoom in and then go ahead. So the takeaway is that in a macro structure, typically we will get an idea of how the features in that particular material would be arranged, and what is the pattern, so on and so forth. And one has to really focus on this particular scale, which will be in terms of millimeter, right? And then in terms of microstructure, for example, we can see that um, so it is again from a titanium alloy, which is a alpha plus beta phase combination, and then such kind of details one can get from this particular microstructure. And then you can see that the scale now has been reduced to a micron scale, and then the features which you can see from this microstructure would be of this micrometer in length scale. And then one can do a different types of analysis, like understanding what is the grain size, and then the phase analysis, so on and so forth, right? So that kind of a detailed analysis can be done when we move from macro structure to microstructure, right? And then now coming on to the nanostructure, where the nanostructure typically can be seen by using transmission electron microscopy. It is another high-end version apart from our scanning electron microscopy, and this is again from a titanium alloy. So you can see that the scale now has been reduced to the nanometer scale, and essentially here this is particularly called as dark field transmission electron micrograph. We can also get bright field. So it is just a technique to see the features in a better way. Okay, so with this, what we can see is that all this bright spots that we see are all corresponding to grains, or we can also call them as crystallites, right? So so all these grains or the crystallites that we see would be in the order of nanometer, right? So now we could understand right from the macro structure to nanostructure, the features are being now more resolved by using appropriate characterization technique, right? So that is one has to really think of while studying or doing research with this kind of material. So obviously we can't see these kind of nanostructures with your optical microscopy because of its limited resolution. Okay, so now as I said, as we have the idea of now the different types of structures, right? And the most of the engineering materials, right, which is used in various application, it could be in a aerospace or in an automobile where this crankshaft being used, and again this is a casing used in a aircraft engine, and for example in a biomedical implants, right? This is again in a, aerospace engine component where you have a compressor blade attached to your disc, and even in an offshore industry. So we see that the different types of engineering materials being used in various kind of application, right, from your aerospace to biomedical to offshore, and they are all being now subjected to different types and in fact maybe a very harsh service operating condition, right? Because of which the material tends to undergo failure, uh, especially from surface point of view, when the component is subjected to mainly for let's say in this case offshore industry, it could be because of corrosion kind of surface damages, the material can fail. And in this case compressor blades, because it always during the service condition keeps rotating and subjected to cyclic loading, we can expect that fatigue kind of damage again, that is right which initiates from the surface of the blade. And again your crankshaft, for example, which is also subjected to cyclic loading, so you can expect the failure or the damage to initiate from the surface. So what I'm trying to say is that in most of the condition, primarily when the components are subjected to cyclic loading, or when they are subjected to some kind of mm, um, a liquid environment, right? Or when they are subjected to wear kind of situation, so the damage is prone to happen from the surface, right? So then that being the case, can we classify them like, for example, what is the material failure, right, in different categories, right? Like for example, that can be understood from this flow chart, where we can also call it as the material loss, in other words, as the loss of usefulness of the material object or the component. And primarily they have three different categories. One is obsolescence, where your component becomes obsolete, right? And then the technological development happens, and then the current component might not be suiting for the given application. So then the material or the component becomes useful. I mean, it is not useful. Failure or the fracture which happens, that is subject different kind of mechanical loading, which is roughly about quantified as 15%. And you can see that the surface deterioration, which I exactly emphasized in the previous slide, the damaging mechanisms such as wear and the corrosion, which primarily happens or the starts from the surface, and then it starts to deteriorate or damage the component, and then usefulness of the component can be lost. So you can see that 70% among this survey comes under this category of surface deterioration. And when we classify them further, you can see that the wear or the tribological damage amounts to roughly about 55%, and the corrosion is 16%, sorry, 15%. And then again, from your wear, we can also classify them depending on how the two different components, when they are in contact and subjected to relative motion, what kind of damaging wear mechanism can happen. Like it could be adhesive, abrasive, and corrosive, and surface fatigue wear. So these are all some of the modes through which this wear primarily initiates, and then you tend to see to that the loss of usefulness of the material or the component takes place. And so this being the case, then it really throws a greater amount of challenge for material scientists as well as the research community to mitigate this particular surface deterioration or the damage, which is quite significantly affected to an extent of 70%, right? So how do we do that is the challenge, and then that is what we are going to look at from now on with the rest of the slides, right? So this is just to give you various mechanical system or the parts which are let's say undergoing different types of damages. Like for example, this ball bearing, right? So due to poor lubrication, one can expect the inner race being damaged with the material removal, and which is again part of wear damage. And this another example of a gas turbine blade, where this is the initial condition before it is being deployed into the system. And since this gas turbine engine is going to operate at very high temperature, we can expect there could be hot corrosion or hot oxidation, because of which the material loss or the surface damage can happen. Sorry for that. Even in the case of wind turbine blades, because of this lightning and other aspect which takes place, the material undergoes loss. And in the case of automobile engine, where you can find this because of this reciprocating motion of your piston along your cylinder walls, you can expect that this piston ring gets worn out, which is also from the surface. And even in the case of hydropower plants, where we see that different types of components are being eroded, which again starts from the surface. And even in the case of cutting tools as well, when we are using them for machining, let's say, the workpiece, so you tend to see to that the tool gets worn out, right? So those are all some of the damaging mechanism starts from the surface, and that is what I want to emphasize. And this is just to give you at a closer look in the industrial application of your propellers or the valve seat that typically used in, for example, in a hydropower plant. So you can see that this cavitation damage which happens on this particular surface because of the pressure difference, and then also it will be actuated by the silt particles. So eventually the material will be removed, and then if it is not properly inspected, we can expect that the material to undergo failure, right? So which can cause a significant catastrophic kind of malfunctioning to the system. And even in the case of, let's say, in agricultural kind of equipments that we use, where we try to use this auger, which is a heavy duty auger, being, try to dig or trying to excavate the sand particles, then subsequently the sand particles being very harder, and they are primarily SiO2, right? Quartz, which is a very brittle or hard in nature, and then they can try to abrade these surfaces, even in the case of, let's say, some earth moving equipments, where it will be used to transport harder ores or the mines from a mining industry. So eventually this teeth portion will be getting abraded due to those hard particles. And for example, pump shaft, which is being getting failed because of this corrosion fatigue kind of phenomena. You can see that the crack has initiated from the surface, and then it propagates interior, and then subsequently it undergoes to a fatigue failure. So the point I'm trying to emphasize from all those things is that it starts from the surface. So when we look at even the implant materials that is used in our inside our body, right? There are lots of implant material, basically metallic kind of materials like titanium alloys are being used nowadays. So they are also being subjected to our body fluid kind of environment. And when we actually for example, during let's say running, walking kind of situation, we are actually inducing a lot of mechanical loads onto this implant. So because of which you tend to see to that the material get worn out, and then there could be some event that these wear debris can react with our body fluid, and then that can cause health related assaults, right? So the idea is, can we have some sort of mechanism or a kind of some nanostructured coating onto this implant, so that we can actually protect, for example. That is a goal. And the number two is, we want to of course enhance the service life or the life of these implants, or for example, in the previous case, the mechanical engineered components, the life has to be increased, so that there won't be any frequent maintenance required, and subsequently we can have a better efficiency of our mechanical system, right? So even for example, the corrosion is a very good example, which could be seen right from your let's say shipping to the gas pipeline. So it is more like, omnipresent, right? So you can find the corrosion to be present everywhere, right? And the damage has to start, I mean, it will start from the surface, right? So that is the point. So by going through previous engineering components example, what we are trying to say is that the surface of the material or the component really matters, right? And one has to really engineer this particular surface so that they can resist the different types of damages when the component is subjected to. It could be a wear kind of loading situation, or a fatigue, or it could be a corrosion, right? So on and so forth. So that is the point I want to make from the previous slides. So going forward, we can see that how we are going to look at the significance and the need for the surface nanostructured material, right? So what we are going to look at is trying to understand the power of this surface nanostructured materials, and then can we use it for our convenience for improving the life of the components, primarily the mechanical engineering components that we saw in the previous slide, right? So now quickly to look at, for example, the significance of surface nanostructured materials. We have seen that at the nanoscale, the grain size would be in the order of 10 power minus 9 meter. So due to which this particular grain size being so small can be a potential strengthening mechanism for the material, right? So we know that as we decrease the grain size, the yield strength of the material can go high from a very well established hall patch relationship, right? And as I said, the hardness of the material can also be increased the moment when we have this, and the heel strength of the material can be increased because of this hall pitch relationship. So then, that being the case, we can actually deploy these surface nanostructured materials for a application which requires high strength, and subsequently can bear the high amount of mechanical loadings, right? So that is what we are trying to propose. And then now we can try to look at what could be our, how this surface nanostructure could materials could be used, and why it has to be used. So we have learned through previous slide that the failure at the component actually starts from the surface. Primarily it could be a fatigue damage, wear damage, or a corrosion. So in the wear damage, we will be more focusing on this fretting wear. I'll emphasize that when we go into that particular slide. So all this damages mainly starts from the surface, and then by using this surface nanostructured material, right, we can obtain superior mechanical properties like increase in hardness and modes which it will operate. One is the fatigue property, right? So both in both the phase, they will try to spend a certain amount of life of the component. So thereby, if we can increase both this crack fatigue crack initiation, for instance, one can really improve the fatigue property, and that can be achieved by the moment when we have this grain size gradient microstructure onto the material, right? So this is how your grain size microstructure, grain size gradient microstructure would look like. So as I said, on the top surface of the material, we will have a nanostructured layer like this, and in the bulk, you will have coarse grained matrix. So basically, this particular nanostructured material is going to be helpful in increasing the fatigue crack initiation. So the crack has to initiate, for which if you make the material harder, the initiation resistance will go high, right? And thereby we can improve that particular part of phase of the fatigue life, the fatigue crack initiation life. And let us assume if the crack has initiated and then it will start now propagating, and the propagation will be easier the moment when you have these kind of finer grains, but the propagation will be delayed, or the resistance will be offered the moment when you have coarse grain, because the coarse grain will have better ductility, thereby it will provide good toughness, thereby the crack will starts to deflect, and then it tries to take a longer path, thereby the crack propagation resistance will be more. So in totality, what we can say is that the moment when we have these kind of grain size gradient microstructure, we will have both the crack initiation life as well as proper crack propagation life are being improved. So that is one of the advantage the moment when we have these kind of surface nanostructured material onto the component surface or the mechanical parts, right? So now we understood that now having a surface nanostructured onto a component will be beneficial for especially for wear and fatigue kind of application, right? So now how do we manufacture them, right? So that is what we are going to look at from this slide. So what are the manufacturing approaches? And this particular nanostructured surface can also be called as surface nanocrystallization as a key terminology. People use it in the literature, in place of both interchangeable. And now there are two approaches, manufacturing approaches to arrive at this particular nanostructured surface. One is bottom-up method, and by the time by this time you might have guessed how this technique would be working. So essentially your most of the coating and deposition technique comes under this bottom up method, in which what we are trying to do is when you have a material A, and then when you are trying to deposit or coat a material B which is of nano size or nano crystalline in dimension, then apparently you are going to have nanocrystalline B material on a material A, which could be a coarse grain, right? So that's how we get a grain size gradient kind of a microstructure, right? So this is one approach, which is a bottom-up method. Bottom-up method is because we are depositing layer by layer, okay? Like you are building from the building blocks of particles. That's why bottom-up method name. Right, but now you also have what is known as top-down method, right? Which is slightly different from this bottom-up method, in which what we are trying to would be doing is that when you have a material A, we will try to employ severe mechanical load, or we will also call it as severe plastic deformation, which is also very commonly used terminology in the literature. And when we employ this severe plastic deformation onto a material A, what is going to happen on this material A, in the surface of the material, whatever the coarse grain which was there, they are going to now get broken into smaller grains in the range of nanocrystalline material, and thereby you tend to see to that on the surface you will obtain surface nanocrystalline layer, or it can also be called as surface self nanocrystallization, because you are using the same material in order to transform the grain size, right? So that we call it as the top-down method, and the name is has been evolved because we are trying to employ certain amount of mechanical loading, and then we are breaking the bigger grains into smaller. That's why top-down method, right? So now, if you look at from the bottom up method, these are all certain disadvantages these method has, right? Like for example, you can encounter porosity, like when you start depositing, if there are certain gaps, so that is what we are going to avoid. We are going to call it as porosity. So you can expect the porosity to be there with this technique the moment when we employ. And we can also expect there could be a contamination, like basically what we are doing is we are trying to deposit material B on a material A, and you can see that, you know, at the interface there could be mixture of A and B, which is undesirable. That's what we are calling it as contamination. And the third disadvantage is that especially at this particular interface, the adhesion between the coating and the substrate is very key in order to decide the performance of this particular nanostructured surface. So or typically when you have some voids or the contamination, obviously the quality of this interface will degrade, and eventually the adhesion issue will come, and then it will peel off. So these are all certain disadvantages under this category. But however, when we look at try to from the top down method approach, all this disadvantage which was there in the bottom up method can be overcome by this top down method. Like for example, there won't be any issue of porosity because we are not depositing any foreign material, and there won't be any contamination issue. For the same reason, there is no deposition of foreign materials, and there won't be any issue of this addition because we are not at all trying to coat or deposit any other additional material onto the components, right? So that's how this particular top-down method has an edge over bottom-up method, especially for producing this grain size gradient kind of microstructure, which is more beneficial in terms of, let's say, from the hall pitch relationship. We can understand that, for example, if you want to increase the hardness, right, at the surface level, so you can find that the hardness at the surface would be significantly high because of when you have this particular smaller grain size that you see. Because of your hall pitch relationship, you will tend to see to that the hardness will be higher. And if you slowly, try to move away from the surface, the hardness tries to decrease, and then it tries to reach the parent material hardness. So this particular process of reaching from a coarse grain to a nanocrystalline grain, we are going to call it as grain refinement, right? So grain refinement meaning we are essentially trying to break or subdivide these bigger grains into smaller grains, right? So that is what we are going to call it as the grain refinement technique. And essentially this top down method is very popularly or very commonly employed to perform this particular grain refinement technique, especially from the severe plastic deformation route. We will quickly see that what is that severe plastic deformation. So now in the rest of the slide or the topic of this talk would be covering on this particular top down methods, what are the techniques available, and how it can be characterized, what are the changes in material property, microstructure, and also from the application point of view, like wear and fatigue will be dealt in detail as we go along, right? So now, as we looked at the significance and the need for nanostructured materials, and also we looked at there are two basic approaches, and among them, top-down method is the most feasible and kind of useful in obtaining the desired end application or the property onto the mechanical parts. So now quickly we will be going through what are the processing techniques which adopts this top-down method, right? So For example, again, just to emphasize through this top-down method, we have seen that these are all the advantages one can have from the previous slide compared to bottom-up method. I don't want to emphasize that again. Now, quickly, we will get into the techniques. So the first technique is this high-pressure torsion, or HPT. It is also called as HPT technique. And this particular technique schematic is shown here. So essentially what happens is we will try to place our sample right between two anvils, right, the lower and upper anvil, and then apparently we will try to apply load, and also we will try to rotate the lower anvil, right. So because of which, what is going to happen at the surface, right, there is going to be a huge amount of severe plastic deformation will be activated, because you try to see to that the grind refinement essentially takes place with this particular technique. And quickly, the process sample, when we try to use it for characterizing it through a TEM kind of a technique, we can see that this is a transmission electron microscope, in micrograph of this particular aluminum alloy. After this HPT deformation, one can find that the grains that we are seeing, for example, these are all some of the grain particles or the features that will be there in the material. So essentially the surface of the material now being transformed from a coarse grained state to a nanocrystalline state, right. So this is one of the technique which uh, people are employing it to generate a nanostructured surface material synthesis. Okay. And the other technique is air blast short peening, or just a short peening process which we are aware of. And we know that in the short peening we will employ very tiny small steel balls which will be made to propel through a compressed air with a predefined velocity, and then they will go and impact onto the surface of the material, and thereby the severe plastic deformation happens, and then you will see that the grain refinement will take place. So this is just to give you a quick characterization result of this process, the short peen sample. So this is the treated layer, and the micro hardness which people have carried out with which is closer to this treated surface. You can see that it is almost like 6.8 GPa, and at the bulk you can see that this is the parent material hardness. So at least you can see that a significant increase in the surface hardness once we do this treatment. And this is the peened layer or short peened layer, where you tend to see that the grains are being compressed and deformed, and which is also, we call it as work hardened surface. And this is the unaffected bulk microstructure. And subsequently, this is the transmission electron microscopy image, where you can see that the treated surface layer, when they do this TEM, we can find that the grain size now being uh, reduced to nanoscale, right. So this is another technique which people also employ. And there is another technique which is called laser peening, right. So this laser peening is also comes under this category of severe plastic deformation. And typically in this process, what people do is they try to irradiate the metallic part or the component with a very high laser radiation. And before doing that, there should be a certain you know preparation of the sample has to be performed. One is we need to have what is called as the sacrificial layer. which is typically paint, or people also use this PVC insulation tapes, which will be a sacrificial layer. And the purpose of this particular sacrificial layer is to avoid, for example, melting or heating of the sample, because at the moment when we employ very high energy laser radiation, there is a chance that the material surface gets melting or heating, that can induce undesirable tensile residual stress. So we need to take care of that, for which people make use of this uh, sacrificial layer, which is primarily made out of paint or PVC insulation tapes. The other precaution or the preparation before this laser irradiation, which we need to take care, is that we need to have a water curtain. Okay, so basically the water will be made to flow onto this particular metallic sample. That is primarily done to confine, or it is used as a confining medium to increase the peak pressure. So what is the peak pressure? I'll come to that now. When we irradiate this particular laser radiation onto the sample, what is going to happen is, immediately at the vicinity of the surface, there is going to be a high plasma pressure which is going to get developed. And these high plasma pressure is the source of performing our severe plastic deformation. Now those pressure has to be diverted into the material, of the bulk of the material, because there is a high chance that these plasma pressure will also try to act away from the surface of the material. If that is happening, then we will be losing the pressure intensity, right? So in order to avoid that, we will try to confine or arrest this particular movement of, away from the sample, this plasma pressure to act. We will try to confine them by using a water medium or the water curtain. Therefore the plasma pressure tries to now only propagate towards the sample, because we have confined the other direction. So thereby the intensity of the pressure shock wave which will penetrate into the sample, right, which will be has to be higher than the yield strength of the material. Thereby there will be localized plastic deformation happens, and then it will introduce compressive residual stress, as well as severe plastic deformation is set to occur. And quickly, if you look at the TEM image, people have observed that there's a formation of nano crystalline kind of a transformation onto the treated surface, and quick hardness measurement performed on this sample shows that significant amount of hardness, surface hardness, has increased, and it decreases as we move away from the treated surface. So this is another very interesting and commercially used technique. In fact, um, leading aerospace industries like Boeing and Airbus, they use this particular technique for peening their turbine blades or compressor blade, because they generate this compressive residual stress, which is good for fatigue kind of resisting fatigue kind of damages. So the other technique is that surface mechanical attrition treatment, which is also in short called as SMAT process. So basically, this is the schematic photographic view of how the total setup appears. So this is by and large very similar to short peening process, okay, but there is a slight difference in terms of operation. So you can see that this is the sample part, and the sample will be fixed at the top. Like this is the schematic, you can see this is the part, and the steel shots are placed at the bottom, and the sample will be placed at the top, right? And then subsequently this two sample part will be now connected with the vibration generator, and then subsequently this vibration generator is connected to an electric motor, and of course there will be a provision of this vacuum line which is given when we perform this particular treatment on some highly reactive materials like titanium. There is a tendency to form oxidation layer just to prevent that, people also use this vacuum line so that this extent of oxidation can be reduced. That is one thing. And now the process happens in the following way. Like, for example, when this electric motor rotates, this vibration generator is going to introduce, like for example in this schematic you can see to and fro motion. Thereby what is going to happen, the steel balls which is placed at the bottom of the steel part are going to get excited, and then they go and impact onto the material surface with a very high kinetic energy. Thereby you can see that very similar situation that happens. The short peening process can be expected. Thereby the severe plastic deformation happens, and then a nanostructured material formation takes place onto the component surface. And quick hardness measurement will tell us there is appreciable significant hardness increase at the surface of the treated layer, and then it decreases as we move away from the surface, right? So just to give you some of the insight, some more insight onto this particular technique of SMAT. There are several key features makes this process really affordable and reasonable to use for generating this severe plastic deformation by introducing large amount of strain. And we are going, because of the severe plastic deformation, there is going to be accumulation of plastic strain, and then eventually because of this plastic strain there is going to be a large amount of defects. Like for example, you can see that before performing this treatment, defects like dislocation will be randomly located in a grain, and then the moment accumulation of this large amount of defects happens, they starts forming a boundary. Like they come together and then form a boundary. Thereby now a single grain now has been divided into two small grains. So this is the mechanism of grain refinement, which happens by dense dislocation dense walls or dislocation angles, and thereby the nanocrystallites happens or develops at the surface, like through this subdivision, right? So now quickly, if you look at if we do this SMAT process, we are going to get this grain size gradient microstructure, where you tend to see to that deformed layer zone as well as the refined grain size, and at the bulk you will have a strain-free coarse grain matrix. And if you quickly look at or measure the strain values, right, like from the surface to the bulk, you can see that the strain will be significantly higher at the treated surface, and then it starts to decrease towards we move towards the depth of the sample, and thereby this significant amount of strain is responsible for generating nanostructured layer, which will be in the order of 10 to 50 microns. And then beneath that you will have a refined grain structure, because still you have this strain being acted onto this zone, and there will be a deformed coarse grain layer, and then eventually you will have an unaffected coarse grain matrix. And you will also see that the strain rate will be significantly high, and that's how this severe plastic deformation mode is actuated. The moment strain rate is going to be high, it will try to generate a large amount of plastic strain in a given point of time with a instantaneously, right? So that is also one of the key reason why this kind of nanocrystallite formation gets developed onto this sample. And now this particular slide is to just to elaborate on what are the effects this SMAT process can induce, and what could be the anticipated benefits or the advantage one can think of, right? Like for example, you can see that the moment when we have this nanocrystalline or fine-grained structure onto the surface, it can first will be benefited in terms of increasing the tensile strength and the surface hardness, and it can increase the fatigue crack initiation resistance, as I was mentioning earlier, and it also can increase the wear resistance. From our AICTE-STTP law, we know that increasing the hardness, we can obtain better wear resistance. So these are all the benefits of the moment when we have this nanocrystalline layer. And we also have this strain-free coarse grained matrix, which is unaffected, right? As I told, this will have a good amount of ductility and toughness that is going to increase your fatigue crack propagation resistance. And the increased hardness, for example, at the top layer or the top surface is going to be increased for improved fatigue behavior, particularly the fatigue crack initiation, and reduced wear rate, and also the decreased adhesive component of friction coefficient. So typically, if you do a wear test, we will measure what is known as friction coefficient, coefficient of friction, COF value, which primarily has two components. One is adhesive component and the deformation component. So this adhesive component is undesirable, and that can be decreased the moment when you have very high surface hardness. And as I said, it is going to also produce the compressive residual stress onto the surface, like in the case of laser peening we have seen. Similar kind of thing is also possible in SMAT process. It is going to generate a compressive residual stress because of a non-uniform plastic deformation which happens at the surface, and there is no deformation happens at the bulk, because of which this compressive residual stress develops, and due to which the improved fatigue behavior can be obtained, and also improved wear performance can also be obtained due to the fact that when we have crack which is getting initiated because of the material removal during wear process, and when that crack has to propagate, the moment when we have compressive residual stress, we can actually mitigate or have a crack closure kind of a effect, and thereby we can improve the wear performance, right? And this particular rough or dimpled surface, although I have not shown, we will be looking at that. When we do this SMAT process, what is going to happen is beneficial, especially from the point of view of decreasing the friction coefficient in the wear resistance, wear testing scenario, and it can also reduce the, for example, wear rate. And we also have this work hardened layer in the SMAT process, which will be getting generated. That is again, as I told, beneficial for both fatigue and wear, and it can also retard the growing fatigue crack. So these are all some of the advantages or the benefits one can expect because of these effects which is induced by the SMAT process, right? So we will be having a closer look at how this fatigue and wear resistance are improved by this SMAT process in the upcoming slides. So now quickly, I just wanted to give you or have a comparison between this mat and short pinning process. Although I said this mat process is very similar to your short pinning, these are all some of the differences one can expect. Like for example, in the case of short pinning, you will have the short size of the steel balls to be in the order of 0.25 to 1 mm. Apparently, in the case of SMAT, you can see that it will be slightly bigger, right? In the case of a SMAT, it will be 2 to 10 mm of the ball size can be used. And if you look at the short velocity, because of its very small size, you'll be able to obtain very high short velocity. But in the case of SMAT, you will have a very low velocity. And if you try to look at the kinetic energy which will be obtained, right, in the case of SMAT, since we are using very bigger size of the ball, we will obtain a higher kinetic energy, which is responsible for generating the severe plastic deformation. And in the case of short pinning, it will be slightly low because of the small size of the balls that we are using. And in terms of this impact directions that we are going to have during the processing would be more like, in the case of SMAT, it will be multi or random directional impact, which is one of the very key aspect of this SMAT process, like for example, the ball comes and impacts the surface of the material, the deformation can happen randomly. Like for example, this ball can go and impact here, and this ball will impact here, this ball can be here and here. So you will generate multiple location, the plastic deformation will be actuated. But in the case of your short peening, since it is a unidirectional or single directional impact, you will tend to see to that it is a directional impact, because of which the extent of severe plastic deformation that we want to induce onto the material sample will be significantly lesser compared to SMAT process. And of course, this is surface roughness will be generated from your short peening as well as SMAT process, but slightly in SMAT, the surface roughness value will be lesser. Okay, so now this particular slide is going to give us between the comparison of this SMAT and short peening process. If you can look at this ball size or the short size that we are using in the case of short peening and the SMAT, in short peening it is less, and in the case of SMAT it is more. And it can be used in this particular analytical equation, which was developed by Hertz, and he proposed a theory called Hertz theory. And from there, this particular Hertz, nothing but the work hardened zone or the plastic deformation depth when we impact or when we process this techniques onto a sample. So this depth is going to be a function of your let's say the density and the velocity and the radius of the ball, and the Young's modulus of your substrate and the ball material. So you can see that as you increase the plastic deformation depth can be increased by increasing your the radius of the ball, which means that when you can use bigger balls, that is especially in your SMAT case, you can induce more kinetic energy, and which will be generating larger plastic deformation, meaning severe plastic deformation, and thereby there is a higher probability of grain refinement leading to the nanostructure is possible, and more depth of work hardened layer can be obtained, and the larger depth and magnitude of compressive residual stress can also be obtained. So that is the advantage or superiority of your SMAT process the moment when we use bigger size of the ball size compared to short peening, right? And yeah, just to give you now a quick comparison between this SMAT and short peening process. This is a finite element modeling people have done, just to give a kind of comparison. What is the kinetic energy obtained in the SMAT process? So this SNH is also called as surface nanocrystallization and hardening technique, which is very similar to the short peening process. So this far, right? So now moving forward, we will try to look at from the application point of view, primarily from mechanical engineering application point of view, and then we will try to conclude. So that is what I've planned in the part 2 of this particular talk, right? So moving forward now, I would like to quickly draw your attention to this technique called short peening, which we looked at. And primarily we know that this short peening process being used for this gear kind of components or turbine blades, primarily to introduce compressive residual stress as well as increase the hardness, right? So you can see that this turbine blades or compressor blades, which is used in aerospace engine, people do this short peening process. And the moment I mean, people also do it for this coil spring to increase their service life. And the moment when we do this short peening, one can expect that beneath the surface there will be a substantial increase of compressive residual stress, and then it keeps decreasing as we move from the surface, right? Towards the depth, if we go, the compressive residual stress will tend to decrease. And quickly, this is what happens actually at the process mechanics point of view. Compressive residual stress will get developed the moment when we do the short peening process. And there is also going to be a cold work which is going to generate, which we also call it as work hardened zone or layer. And because of this tiny shots coming and impacting onto the surface, there will be surface roughness increase after the process is done. So these are all some of the characteristic of this short peening technique. And now I just wanted to draw your attention for this microstructural interaction. Like the moment when we do this short peening process, it is also equally holds good for the techniques that we saw, laser peening and SMAT process. Primarily what this particular short peening surface does is that it will act like a crack arrestor. Like for example, if you assume this is the surface of the material, and then when we try to apply a load, and if you see to that there are some defects or some undulations or surface irregularities, if it is there, then because of this tensile kind of load application, the crack has to now propagate through the material, and then subsequently you tend to see to that the material fails, right? That is the usual scenario when we don't subject this material for a short peening, right? But the moment when we do this short peening process, what is going to happen is that you can see now this bigger grains have been refined into smaller grains, right? And because of which we are going to have this strain hardened zone, and also the presence of compressive residual stress. Thereby the crack which is initiated, or for the crack to initiate, there is going to be a lot amount of resistance offered by this compressive residual stress, and as well as the strain hardened zone, right? And then subsequently, let us say it has initiated and then propagated, and when it comes in between, I mean into the material, let's say bulk region, because of this coarse grain, it is going to have deflecting kind of scenario, because of maybe one reason is that you have coarser grain which has a good amount of ductility. And the second thing could be if there are some primary precipitates in your material, right? Then they can also become like a obstacle, and there could be more like secondary precipitates can also become like a obstacle, right? So subsequently they will start deviating or deflecting this crack, thereby it tries to take more time to propagate and then induce the fracture, right? So and even the grain orientation will also play a role in resisting the crack, and the grain boundaries will also play a role in resisting the crack propagation. So apparently what I'm trying to emphasize that this crack initiation thing is going to be delayed because of this presence of compressive residual stress and the strain hardened zone, and the crack propagation will be also delayed because of the various features which will be present in the material, like coarser grain and primary precipitates, secondary precipitates, right, and the grain boundaries. They also play a significant amount of role in delaying the crack propagation. Okay, so this is very important from the viewpoint of fatigue damaging mechanism, how that can be addressed. Like, for example, the crack being one of the culprit to induce the damage or the fracture into the material. So that can be arrested by this short pinned surface, right? So that is the takeaway from this particular slide. Now, quickly, I think uh, you know this short pinning concept, how this compressive residual stress are getting developed onto the material is given here. Sorry for that, I think I wanted to have an underline here that has gone there. It's okay. So there is a, in fact, this law of residual stress, actually what it says is that the sign of the residual stress which is getting imparted to the material is opposite to the sign of the non-uniform plastic deformation that is caused the stress. Like, for example, as we know that when there is an impact onto the material, there is going to be stretching of this surface, top surface is going to happen, which is more like now tensile stretching, right? So that particular thing has been caused by this particular impact, and then as a result, compressive residual stress are going to get developed onto this material surface, and that's what is being conveyed by this law of residual stress. And now quickly I'll take you through the case study, primarily for this Inconel 718, which is one of the aerospace material which is being used. And the goal is to, let's say, increase the surface hardness. And you can see that this is the Inconel 78 or alloy 78 material information, chemical composition, and its hardness in double edge condition, and this is the microstructure of that particular material. And the moment when we do short peening on the surface, you can see that now at the top surface there is a deformed zone, and the bulk is not deformed, and thereby you can say that this particular treated or peened layer will have now higher hardness because of the grain refinement. And now quickly one can do this XRD characterization onto this short peen layer and try to calculate to untreated sample, and you can find that the compressive residual stress is also increased compared to untreated sample condition, right? So quickly you can appreciate the difference the moment when we do this short peening with respect to these changes from the microstructure to compressive residual stress. And if we do a TEM analysis onto this short peen layer, one can find that now grain size has been decreased to a nano regime. All this bright spots correspond to the crystallites on the treated layer. And if we do a quick hardness measurements, primarily it has been done by using a nano indentation. You can see that significant amount of hardness is there at the treated layer, and then it keeps decreasing and then reaches the parent material hardness, and for which we know that this all picture equation is can be correlated, and the grain refinement is the response reason for increasing the surface hardness at the peened layer. And quickly, if we do a tensile test onto these samples, short peened samples, you can see that this is the untreated stress strain curve, materials stress strain curve. The moment when we do a short peening, you can expect, because of that work hardened, there will be slight increase in your yield strength as well as your UTS value, and apparently it can influence the tensile properties of short pinned material. And that is again due to the fact that you have this work hardened zone, and they will be responsible in increasing slightly the yield strength and the UTS of the material compared to untreated material. And quickly, if we look at the performance of these short pin material from fatigue test point of view, you can find that the short pin material will show better fatigue performance compared to your not short pinned, and thereby the endurance limit of this short pin material, it is basically a aluminum alloy. You can see a significant amount of improvement in fatigue property can be obtained the moment when we do short pinning. And the reason for that is that two things contributed for better improvement of this fatigue life. One is presence of compressive residual stress and the work hardened zone, or the nanocrystalline layer which is being formed. And that is about the short pinning case. Now we would be taking a quick look at the influence of this SMART process, and we have seen this, and this is a quick SMART process parameter which is being used for this particular case study, where you can find that 5 balls being used, and they have used four uh, different treatment duration, and the vibration frequency is 50 hertz, and they maintained vacuum while performing this particular SMART treatment. And now quickly the result, if you look at um, from untreated or unmodified, and when you increase the treatment duration from 50 to 60 minutes, what you can find is that there is an appreciable increase in the surface hardness. There is a going to be monotechnically increase the surface hardness value as well as the compressive residual stress as you increase your treatment duration. And you can also find compared to this unmodified or untreated sample, there is an appreciable increase in surface roughness after performing this SMAT treatment, right? And yeah, I think this is the same thing here, but here I wanted to focus on when we try to select this particular 30 and 60 minutes and try to carry out this surface hardness profiling. One can find that the 60-minute treated sample shows higher surface hardness value, also much higher value at the deeper surface, so compared to 30 minutes treated samples, which is in line with the grind refinement which has happened, and the Hall pitch relationship is the responsible reason for increase in this hardness. And if we quickly do this X-ray diffraction technique onto this treated sample, one can find that this is for a titanium alloy, which is in annealed condition. We know that the FWHM, or the width of the peak, is one of the indicator to tell us whether there's a formation of nanocrystallites. Like for example, if the peak broadening is happening as you increase the treatment duration, so we can say that this peak broadening can be attributed to the presence of nanostructured layer or fine grained layer, and also the presence of micro strain. And quickly, if we try to look at the surface morphology of this treated sample, one can find that this is the unmodified sample. As you keep doing this mat for different treatment duration, the now fresh surface, smooth surface, as being getting damaged or roughened because of this ball impact. And you can see that with 60 minutes the impact is more, and there are some material being stretched, right? And this is the consequence of SMART process, which will in a way increase the surface roughness, and that is what we looked at in the table, where SMART treated sample showed a higher surface roughness value compared to unmodified. And quickly to look at and understand what is the impact on the work hardened layer for different treatment duration. So you can see that this is unmodified layer, and at the top surface where the treatment has happened, the layers are being compressed, and the work hardening are taking place, and the depth of work hardening is increasing the moment when we increase the treatment duration, which is quite obvious because we are inducing more and more plastic deformation, thereby more and more deeper work hardened layer will get generated. And this is the quick investigation on TEM analysis. One can find that there is a formation of this nanostructured layer on the treated layer in the case of SMART treated for 30 minutes as well as for 60 minutes. So this is evident and correlatable with the X-ray XRD investigation, which is seen the peaks are getting broadened, and then this actually tell us the grains are refined into nanoscale. And the nano indentation hardness measurement, of course, we saw that, and which can be correlated with the work hardened or harder surface from Hall pitch relationship. This increase in hardness has been, obtained. And now, quickly looking at the wear resistance performance of this particular SMART process, right? So what has been done is that here the fretting wear resistance is being evaluated. So what happens in, for example, fretting wear process is that this particular reciprocatory motion that we see will be in terms of micron level, micrometer relative motion will be given to, the sample which is of interest against a harder counter body or a ball. Usually it is done at a ball on flat configuration by following this ASTM standard. So due to which you expect the material to wear out, and then eventually you try to measure what is the wear loss, and then try to comment on whether the SMAT treated process is having a beneficial effect in improving the wear performance of these material or not, right? Like quickly, if we look at the result of this untreated and SMAT treated for 30 minutes and 60 minutes, one can find that now this particular information would be captured by increasing the normal load right from low normal load to a higher normal load. And this is the typical characteristic. Like for example, the wear volume is going to increase till certain value of normal load, and then further it will start decreasing as we increase the normal load. And this is the typical characteristic of a fretting wear kind of a situation. So what is going to happen is that, like for example, at lower normal load, we tend to say that there is going to be a gross slip regime prevailing, which means that you have very less normal load. When you have this reciprocating motion, you are actually offering less resistance for this movement with less normal load. Then thereby we go say that gross slip. Slip is nothing but the movement of your material, and thereby we call it as gross slip to prevail under the less normal load. And slightly when we increase this normal load, let's say to a value of some 10 Newton, what is going to happen is the partial slip, which means that there is going to be slight resistance offered by this increased normal load. Thereby the relative motion of this particular substrate is going to be mitigated or prevented. Thereby we say partial slip. And if we further increase this normal load to a value of, let's say, 20 Newton, then it is almost like a no slip condition, which means that we are actually making this particular titanium alloy movement being constrained, which means that it is as good as now both, although you induce the displacement, because of this higher normal load, this titanium alloy substrate is not able to move. or there is no reciprocating motion offered, because of which there won't be any material loss. That's what you see, the material volume to be very less at a higher load because of this no slip condition. Okay, so this is the typical characteristic that you can see in all the sample behavior. It increases, and then as we increase the normal load, the wear volume decreases. So the takeaway from this graph, one can find that the sand treated sample showed better fretting wear resistance compared to your black colored untreated sample, and which is obvious because you have better surface hardness as well as compressive residual stress on these samples. But surprisingly, what you can see is that this 60-minute treated sample shows inferior or more wear volume compared to untreated samples. Although you can see that in this hardness measurement, the 60-minute treated sample had a higher hardness compared to 30 minutes. So which means that it should show here better fretting wear resistance, meaning less wear volume compared to 30 minutes itself, but it is showing on the other way, showing a very high material loss, that is compared to untreated sample itself. It shows a poor performance in terms of fretting wear behavior. So if we quickly look at some investigation by on this fretted sample, what you can find is in this case of 60 minutes, this is the actually worn out sample. You see a signature of a lot of brittle cracking onto this sample, because the sample has higher hardness, which means that it behaves more like a brittle kind of material response for the given load application. Thereby brittle cracking happens, and then there is a lot of where debris get generated, and then this displacement being very small, as I said, it is in terms of microns compared to your reciprocating sliding wear that you do it with pin on disc or reciprocating, where you have quite large displacement in terms of 2 centimeters or 3 centimeters. But in this case, it is in microns. So thereby this debris which gets generated will be trapped at the interface. Thereby now what is going to happen is that now initially you had 2 body wear situation, but the moment this wear debris are getting generated, you will have 3 body wear situation. So that is very aggressive, and severity wear severity level will increase. Thereby you tend to see to that the wear volume is higher. So the reason for 60-minute is that because of its very high hardness, it has lost its ductility, meaning it showed a brittle response to the applied load. Thereby three body wear situation prevailed, and that's how the material actually performed inferior. And of course, when we do a little bit of when we use the contact mechanics and then try to calculate some contact pressure at this particular location, that also has a significant role in playing aggravating this behavior. And this is a nano indentation plot, which is the load versus depth, is also indication that smaller the area under this curve tell us that the material is behaving more like a brittle or lost the ductility. So you can see that the 60-minute treated sample has lesser area under the curve, thereby it behaved more like a brittle. So the takeaway is that now, which is totally different from our AICTE's law. The AICTE's law says that higher the hardness, better is the wear resistance. But in this particular scenario, we have seen that the poor performance in the case of 60 minutes showing poor wear performance. So what we are going to say is that for a better wear resistance, there should be a optimum combination of both hardness as well as ductility should be there. Thereby we can have better fretting wear resistance. So that is exactly observed in the case of 30-minute sample showing better wear performance because of both combination of hardness as well as ductility. Okay, so that is the takeaway, which is slightly different from the AICTE's law, which says that higher the hardness, higher the wear resistance, right? So this is quickly just to give you understanding of the same fretting where resistance can be done by using, can be done by using different counterbody material. Like the ball material in the previous case was alumina, it can be also performed by using with the steel balls, and this is the result which use the counterbody. When we use it is going to induce a lesser wear volume compared to the alumina counterbody. The reason being is that there is going to be tribochemical reaction happens at the interface, and there is going to be a tribochemical reaction products which will be brittle in nature, they are moving on to understanding the fatigue lives of or fatigue performance of this smart treated sample. Of course, we know that this testing has been done by using a uniaxial test mode, and you can see that now with respect to smart treated for 30 minutes shows better fatigue performance compared to untreated sample. And here in this case also the smart treated for 60 minutes shows inferior fatigue performance, which is undesirable, and it is very similar to the fretting wear performance what we saw. So if you try to look at from the 30 minutes, what is the reasoning showing reason for showing better performance is that there is presence of significant amount of compressive residual stress in this sample, and also presence of nanostructured layer is there on the samples, and grain size gradient microstructure is also developed because of this matte process in the case of 30 minutes. On the other hand, for this 60-minute treated samples, you can see that the inferior performance can be attributed to the micro cracks that is present on this sample. Like, for example, the surface morphology that we saw in the previous slide, you can see that at the 60-minute treated sample, when we zoom in and then see, there are quite a number of micro cracks which is already there, and the presence of these micro cracks on these samples behave like a potential stress concentration areas or location. Thereby the beneficial effect whatever was there in this 60 minutes, it had compressive residual stress, nanostructured, grain size gradient, all those things being nullified by this presence of micro cracks, and so that's why it showed a inferior fatigue performance compared to the smart treated 30-minute sample. Okay, so yeah, that is the takeaway, and I just wanted to draw your attention quick one-on-one comparison between what happens when we compare the smart process with the short peening, right? Although we saw these case studies individually, this particular slides will show one-on-one comparison, and that will tell us which process is superior, right? So as I said, in the case of smart process, the multiple random directional impact is one of the key feature which we will get when we use the smart process, that is benefit us in inducing the severe plastic deformation in a greater amount compared to short pinning, right? So now this is just to give you different features of grain size gradient microstructure, and one can really design these kind of microstructure by manipulating those process characteristic, and one can get grain size gradient a scheme like this, or we can also get twin thickness gradient like this what is depicted, and also laminar thickness gradient. and columnar grain size gradient. So there are different scheme available depending on the application one can really induce, and also it is material specific. Okay, so this design one can get. And quickly the comparison between the SMAT and short peening, we can see that it is for the same material. It is in Inconel 7 and 8. We can see that the deformed zone is less in the case of short peening, because of very small balls, as well as less amount of severe plastic deformation. But in the case of SMAT, you can see the deformation zone is significant compared to the short peening. And with respect to X-ray diffraction characterization, we can see that in the case of SMAT, less crystallite size and more microstrains are obtained compared to short peening, and surface roughness are by and large high in both the process, but the compressive residual stress obtained would be high in the case of SMAT compared to short peening process. And in both the process, for titanium alloy, we can see that there is a formation of nanostructured layer formation because of the severe plastic deformation which is taking place. And quickly, if we look at nano indentation hardness from these samples, one can find that there is going to be, appreciable increase in the surface hardness in the case of SMAT process, and in the case of short peening, it is going to be slightly less compared to SMAT process, which is because of the deformation zone that we saw in the case of SMAT was higher compared to short peening. Okay, so moving forward, with respect to fatigue life, if we can compare both SMAT and short peening, we can see that the SMAT process shows marginally better performance compared to short peening process. In fact, this arrow shows that the sample did not fail, which shows that the SMAT process is really superior compared to short peening process because of the benefits and the mechanics that we saw in the introduction section of the part 1. And this is quickly just to demonstrate fractographs of the fractured sample to tell us that the crack initiation site, in the case of unmodified or untreated sample, the crack really initiated from the surface. And in the case of SMAT, you can see that the crack initiated from the subsurface, which is a typical characteristic of compressive residual stress. And in the case of short peening, it is also slightly subsurface, but not that deeper compared to SMAT process. And we want to say that SMAT process is superior because this work hardened layer was increased by increasing the size of the ball, which we have already discussed in the previous slide. And I think this result also we saw, right? So now I think this is a last case study that I have as a part of this talk. The laser peening that we saw, case study would be looked at from now on. And this is the laser peening workstation which is being optimized for these parameters. You can see that this is the sample and plasma being generated at the near surface, and this is the water flow which is used to confine the plasma pressure, and then it will be subjected towards the interior of the sample. And quick results, we can see that for surface morphology for unpeened titanium alloy and laser peen, there is not much significant increase in the surface roughness because it is slightly different non-contact method of inducing severe plastic deformation, unlike your SMAT and short peening process. And that's why the surface roughness are not really increased after the laser peening. And if we look at quickly, from the surface roughness point of view, the 3D profile images also shows that there is not appreciable increase in the surface roughness value of these samples after the peening condition. But you can see that when we do some tensile property investigation, that also tells us not much significant difference between the unpeened and laser peened sample. However, for residual stress, you will see that increased surface compressive residual stress are getting developed compared to unpeened sample, which is the characteristic of laser peening. And quickly, if we do a XRD characterization, and then what we will see is that there won't be appreciable peak broadening which is observed from the laser peened with the XRD technique between unpeened and laser peening. And subsequently, when we actually do this transmission electron microscopy, we can actually get insight of formation of this nanostructured layer. And of course, this is a slight detail, deeper detail. In the interest of time, I'll just skip this, and I just want to give what is the mechanism for this nano crystallization, right? Like for example, in the SMAT, we saw that when we have a bigger coarse grain, because of severe plastic deformation, there could be, twin formation and then dislocation formation, and then apparently these dislocations starts to form their own boundaries and subdivision of grains, and thereby we say that subgrain forms, and then eventually the nanostructure takes place, which is a very well established mechanism, how this nanostructure develops. Right. So moving forward, this is again very similar typical characteristic of increased hardness for this laser peen titanium alloy can be seen, and as we move away, the hardness reaches to parent material hardness, and in the case of this load depth graph, one can find that the load under the curve tell us the resistance for plastic deformation or the hardness improvement. Lesser the area value of area under the curve, it tells us that the material has become harder. That is the takeaway. And quickly, the fretting wear resistance of this laser peened sample, one can find that, for example, after doing this test by ball and flat configuration, this is how the wear scar would look like. It is more like this ball will try to indent during this wear process, and it will try to generate this wear scar, and we'll try to measure this diameters both horizontal and vertical, and that's how the wear volume will be depicted. And we can find that the wear volume in the case of laser peening is very less compared to unpeened because of its improved surface hardness. And quickly to look at now, this is the comparison for we looked at SMAT and laser peened, and when we try to compare for this titanium alloy, we can see that this SMAT treated sample shows better fatigue life compared to laser peened, and of course both show better fatigue performance compared to untreated. But we already seen this SMAT treated 60 minutes sample showing poor performance because of its micro crack generation. This is for titanium alloy, and we have seen this micro crack generation. But on the other hand, for alloy 78 or inconel 78 material, all the samples showed relatively better performance of fatigue life, where you can see that in this case of alloy 78 for 60-minute treated sample, there is no such micro crack generation in this inconel 78 because of the fact that this alloy 78 is more ductile and less notch sensitivity kind of behavior for this matte process compared to this titanium alloy. So the point here I want to make is that the SMAT process is material specific. For example, in the case of titanium alloy, it can generate micro cracks, but in the case of inconel 78, because of its ductile nature, it can absorb the impact energy. So that's how the fatigue lives have improved for 60 minutes case. And this is a quick fractographs, which is very common, and where the crack locations are seen for different peened samples. For titanium alloy, this is for alloy 78, and you can see that in most of the case the crack locations is going to be subsurface, which is a typical characteristic. Okay, fine. So I'm finally, I think I'm on time and I have sufficient time for discussion also. This is how I want to conclude my today's talk, saying that the nano-structured layer material has higher hardness and yield strength, and subsequently these nanostructured materials can be obtained by your mechanical route, that is top-down approach. And they have the nanostructured materials have a great scope and potential in mechanical engineering application, primarily for improving the fretting wear resistance and fatigue resistance. So probably I would like to stop here, and thanks for your patience listening. So maybe if there are questions, we can take them.
Thank you, sir. It is a really very detailed presentation, sir. Shall we go with question and answer session, sir?
Please go ahead.
Yes. I request participants to please type your question in the chat box. We will ask on behalf of you, or you can unmute and you can ask directly to our resource person. Sir, one question in the chat box, sir. It is from Professor Gurulingam, sir.
Yeah, please.
Shall I proceed? Yes. Due to mechanical attrition, the surface is subjected to fatigue. How this behavior is interpreted for enhancing surface quality without any post-treatment?
Okay, well, I mean, it's a very good question actually. So in SMAT process, of course, it will call for post-processing because of the fact that it induces rougher surface, right? And that is also is the similar situation adopted for short peening. For short peened process, once the short peening is done, people used to go for post finishing operations like lapping, honing, right, kind of techniques, so that the undulations or the rough feature which is on the treated layer can be removed. Otherwise, such presence of rough feature will be detrimental for fatigue performance, because we know that fatigue is strong. I mean, fatigue has a strong correlation with surface roughness. If you have higher surface roughness, your fatigue life will be less. So what I'm trying to say is that we need to go for post-processing after the SMAT process.
Thank you, sir. This is another question from Professor Durlingam, sir.
Yeah,
how
please.
the fracture toughness of nanostructured layer is differentiated with the core microstructure. And what mechanical test is adapted?
Explain in my presentation was from the viewpoint of the grain size, right? Like, for example, from theory, we know that if your material is, let's say, ductile or tougher, if you look at the microstructure, the grain size will be bigger, right? So that's why as in the materials engineering course, there are several strengthening mechanism. In one of the strengthening mechanism is grain size strengthening mechanism, where we try to reduce the grain size, and then from the Hall pitch relationship, we say that the material has become harder. And other way of saying is that, of course, it has reduced. I mean, if we say that material has become harder, the other way of saying is that it has lost its ductility. If it is lost its ductility, we can also say that the toughness is also lost, right? So from the microstructure point of view, one can comment or interpret this toughness behavior, or the ductility role in deciding, let's say, when you have a crack and how it propagates. That was the first question. Can you please, second part of the question, can you please repeat?
Yes, sir. Yes. What mechanical test is adopted to assess the variation at the interface?
Okay, fine. So, for example, first by visual technique, we will do this optical microscopy where I've shown the work hardened layer and then the undeformed micro, structure or the grain size. So visually we can see that, and then the simple mechanical test is the hardness measurement that we have seen. For example, in this particular case, you can say that by doing hardness measurement up to a value of this 300 microns, you tend to see increase in hardness. That is because of your change in the grain size, and after which it is by and large same as your parent materials microstructured or hardness value. So we can interpret from this hardness measurement that till this particular 300 microns is the work hardened zone, or otherwise hardened zone, or otherwise the material is going to have less ductility or toughness in this zone compared to your bulk of the material. So the simple mechanical test could be a hardness measurement, as which is depicted here.
Thank you, sir. Another question from Professor Kavita. Can we find compressive residual stress for nanocomposites?
Oh, nanocomposites. Well, that is totally different material system I have not really worked on. Maybe it is difficult to answer, because for metals we know that we use this X-ray diffraction technique to estimate the compressive residual stress. But for nanocomposites, since I've not worked on that kind of composite, nanocomposite materials, maybe it is difficult to comment on that. Sorry for that.
Okay, sir. Another question from Prashant Kumar Reddy. What are the possibilities to make nano surface using friction stir processing?
Can you please come again?
Yes. What are the possibilities to make nano surface using friction stir processing?
Well, I mean, in fact, people have observed ultra fine grains, after this FSP process, right? And that is possible, and that's how you will tend to see significant mechanical property improvement. Like, for example, hardness will be better in your processed zone compared to unprocessed zone. And for obtaining nano crystallite size, probably the FSP parameters, like in terms of the tool profile or the RPM that is being used, right? If we can play with that, and also it is depend on the material response for that operating condition. At least I've not come across, maybe it may be there, but I've not come across people talking of nanocrystallite formation from FSP, but it should be possible by optimizing the process parameter. But certainly the grain refinement to ultra grain formation, like for example, people have seen 1 micron grain size and 0.5 micron grain size after doing FSP. And I think it should be possible to obtain nanocrystallites also, but I've not come across it. Yeah.
Thank you, sir. This is another question from Professor R. Naresh. Sir, whether there will be any reaction takes place between balls and treated surface. Also, whether this is going to alter chemical composition.
Well, so there could be that's how we choose this particular balls, in such a way that it will not have this particular chemical reactions or contamination kind of a thing with the substrate material. But there are some research work where people have seen when they use this tungsten carbide balls, right? And they have seen some amount of this tungsten carbide signature on the treated layer, and due to which in fact, I can recollect one of the paper that actually the researchers have focused on fatigue life performance of this smart treated layers, where they have used this tungsten carbide balls, and they have seen inferior or poor fatigue performance because of this contamination issue. So yes, that is possible. Contamination is possible, and one has to really choose this ball material in relation with the material that we want to process. Yes, the answer is contamination people have seen, and it has greater negative implications on the fatigue kind of property.
Thank you, sir. I request the participants. Yes, sir. Sir, one more question from Professor Naresh, sir. What is the suggested ball material?
Oh, well, this is a very open-ended question. It actually depends on the what material we want to process, right? So the key characteristic of the ball that we have to use has to be harder than your substrate material, right? So that is one of the key feature or key property that has to be focused for while selecting the ball. And again, that also going to be correlated or connected with the sample that we are going to process. Like, for example, if we have tungsten as a substrate material which we want to process, and if we are using tungsten ball again, you will see that hardly any deformation taking place, right? So uh, one has to be really very careful in selecting this ball material. It depends on entirely on the substrate material that we want to process.
Thank you, sir. Professor Naresh, sir, if you are having if you want any clarification, you can extend your questions, sir. Please unmute yourself and you can ask questions, sir.
Hello, sir. Can you hear me, sir?
Okay, sir.
Yeah, please, sir. Yeah.
Sir, this is another question from Professor Puring, sir. Yes, sir. Please, sir. Proceed, sir. Naresh, sir, please.
Actually, my question is regarding contamination and chemical reaction only. So for the reason I asked the ball material, whether we can have any generalized ball material that can be used for any material.
No. It is maybe we may not have that kind of a privilege to use only one ball material for all the given samples or the component. It will be material specific, sir. So it has to be chosen because, for example, titanium kind of material, they'll be also very reactive, when we do this process. And during this smart process, inside the chamber, people have measured the temperature to be rising to about 100 to 150 degrees centigrade. Okay, so if not from the contamination from the ball, because of the slight increase in the temperature which is going to happen during this mat process, there is going to be some amount of oxidation or oxide layer which is going to form on the substrate. So that also one has to really look into. So from that aspect also, this chemical reaction and the contamination can enter, not only from the ball material.
We need to take care of temperature also.
Yes. Temperature, and people also make use of some cooling arrangement, like running, water as a circulating or across the sample chamber to maintain the temperature, so that the chemical reactions or the contaminations can be mitigated. So, but it is slightly challenging because in the SMAT process, you have that sample part will be vibrating at 50 hertz frequency. So along with that, your cooling system also should vibrate. So it becomes more challenging. But one can attempt that.
Thank you, sir. Thank you, sir.
Yeah, thanks.
Thank you, sir. This is another question from Professor Gurulingam, sir. While improving the surface quality by severe plastic deformation process, the core is subjected to stress. To retain the core mechanical strength without compromising the surface quality, what kind of post-treatment process are suggested?
So this question with respect to SMAT, right?
Yes, sir.
Okay. So it is well known that we are damaging the surface while inducing this severe plastic deformation and developing this nanocrystallite layer, as well as development of compressive residual stress. So if we look at from the viewpoint of finishing the treated surface, one might look at it has to be a non-conventional way of carrying out this surface finishing, because you can see that in one of the schematic I shown that generally in SMAT, what people have observed is the nanocrystallite surface to be in the order of 50 to 100 microns. It's going there, sorry for that. So because of which yeah, I think here, so you can see that this nanostructured layer is going to be present for a depth of about 10 to 50 microns, or again it is just a guideline value, but again it depends on the material. If your material is soft, and then you can increase this depth to 100 microns, 200 microns, so on and so forth. So if we use conventional post finishing techniques, there is a good chance that you can totally remove off your already induced nanostructured layer. So for which maybe a non-conventional and very precision kind of post finishing techniques has to be thought of. Like, for example, one could be electro polishing, right? People are using pulsed electro polishing technique as one of the technique, which is a non-conventional post finishing technique, where you try to remove in a controlled way maybe a 1 micron layer or 2 microns layer, which is mostly will be your peaks and valleys which will be present on your rough surface. So electro polishing could be one potential technique could be thought of.
Okay, sir. Thank you, sir. I request once again participants, if you are having any question, please type in chat box. Sir, shall we proceed with the vote of thanks, sir?
Sure, please.
Thank you. Thank you for your very excellent presentation, sir. Your presentation added more value for this 1 week STTP program. Really, it is excellent presentation, sir. We have gained more knowledge about nanotechnology and nanosurface characteristics. We are receiving overwhelming positive responses from all participants. Like, it is a very really informative session, sir. Takeaway from your presentations are dimensions of material structures and engineering applications in various surface applications, and significance and the need for nanostructured materials And you have explained bottom-up or top-down advantages and disadvantages in that processing technique, high pressure caution, air blast sharpening, laser cleaning, and surface mechanical attrition treatment like the SMART and its anticipated benefits. Then differences with the various characteristics like tensile test, fatigue test, X-ray diffraction, and the influence of counterbody material on fretting resistance. Finally, laser cleaning, and you differentiated with the other two techniques, nano integration studies, fretting wear resistance, fatigue like spectrograph. It is really very excellent presentation, sir. Thank you very much, sir. So now I request our convener to conclude this session with thanks to our resource person. Requesting, sir. Now I request our head of the department and convener of this program to conclude the session with thanks to our resource person. Sir, convener, sir.
Sir, Madhivanan sir, maybe sir is
Yes,
trying
sir.
to speak, sir.
Okay.
We
But,
cannot, it is not audible. No problem, sir.
okay. Sir, Professor Anand Kumar, sir, sorry for the inconvenience, sir. Sorry is having some technical problem. Thank you very much for your presentation, sir. On behalf of our STTP admin team and management, we are very much honored with your presence, sir. That is very nice. Sir. Thank you, sir. Thank you very much.
Thank you very much. Thanks for the opportunity. It was my pleasure. Thanks.
Thank you, sir. Yeah. Speaker is from NIT Trichy, Dr. S. Kumaran, Professor, Department of Mechanical Engineering, and the topic is nanostructured material synthesis or synthesis of nanostructured materials. Thank you, madam. Thank you.